What's going on, everyone? Johnny Bannon here with Trepa Technologies, and today we're going to finish up domain 2.1, our routing technologies, by talking about and going over network address translation, first hop redundancy protocols, and then also sub-interface on a router. It's just kind of easy. I'm just going to jump into a router and create a sub-interface and be like, hey, this sub-interface is going to be doing inter-VLAN routing for us. So really easy objective there to hit. And then as we go over first hop redundancy protocols, we're also going to talk about virtual IPs, because whether you're talking HSRP, VRRP, or GLBP, they all have a virtual IP address that users are going to use as the default gateway that's going to be assigned to a primary or secondary for the actual routing of that traffic or the forwarding of that traffic. So let's go ahead and begin. So let me zoom my face out here, put it up here in the corner. All right, so network address translation. So NAT is how we take private IPs and translate them to a public IP so that we can have reachability and have internet connectivity from inside our LANs, from inside our home, small office, or campus networks. So there's a couple different ways to perform NAT. We have static NAT, dynamic NAT, and then port address translation. You look at a small office, home office. You look at our typical business offices, our campus networks. We're going to usually have PAT enabled, port address translation, which is going to allow us to have a singular public IP be used for a whole /16, a whole /24, hundreds of private IPs. And we do that by maintaining a PAT table that maps port numbers to the internal private IPs. Now we talk about NAT just as a technology. As a base technology, it just translates IP addresses, private to public, or inside to outside IP. So the security benefit is NAT's going to hide your internal IP addresses. So sometimes we could do this even for like web server farms, or like NAT is used in a lot of proxy technologies, like behind the scenes, right? Where we have a reverse proxy. So we have our forward IP address that's facing the ISP, and then we have our web server farm behind that, and we're doing that translation, right? So NAT can be used on special use cases like static NAT. I've had to put static NAT statements in on my home router to be able to forward traffic to the private IP Raspberry Pi that I have running a WireGuard VPN. So I had to do a static NAT translation that says, hey, if you see anything inbound headed to port 51820, then send that to this private IP address here. That's my Raspberry Pi, and that's where my VPN server is. So there is a lot of use cases for NAT. Now, the most common use case, again, is going to be for port address translation. So that's going to map hundreds of private IPs to a single public IP. Now, if you can see this design here, you can see we have four definitions that can be a little confusing. We have an inside local, an inside global, then we have an outside local, and an outside global address. So let's talk about that. So the outside addresses are going to be the destination, final destination. That's going to be the web server that your user is trying to reach. So the outside addresses here is going to be whatever web server, let's say, if we look at this first, we'll get my pen out, this first entry here, right? And let me just change this to white so it's a little bit easier. This first entry here, right? So this PC is trying to reach this web server here. So it's going to send traffic, right, out to its default gateway saying, hey, I want to go to this web server. So during that initial sending, that layer 3 packet, right? Ooh, that square looks awful. I don't like that. That rectangle, I guess, looks awful. The source IP is also going to be the inside local. This is our original header. And then the destination IP is going to be what's called the the outside local. So essentially what this is saying is, hey, the source IPs are inside local when it's inside our network, in our LAN, traversing our LAN. This is what the packet looks like. It's going to have my private IP, and then the destination IP is called the outside local, because essentially we're saying that packet that's within here has a destination IP of this, so it's our outside address, but it's still local. That packet's still local inside of us, okay? And then once that packet reaches our outside interface, this is going to change. This is going to get translated. So now the source IP is going to be called the inside global. And that's going to be the public IP sitting here. And what we're saying here is essentially that, hey, this global IP that we're translating, because remember, this source IP is changing now. It's going to become 65.160.10.1. That's the translation from inside local to inside global. Because we're still making that mapping, right? Where we say, hey, this is mapped to this. And then the outside global doesn't change because the destination IP address never changes in the life of a packet. So a destination IP is still going to be outside, but now we call it global because now it's going across the ISP. This new packet right here is now, it's global, right? It's going across the ISPs to reach the final destination, going across the internet. Now you may say, okay, but how does this enable us to translate multiple private IPs to a single public IP? Well, let's talk about this. So we see that our inside local or inside global address, the port number is 3000, and we're going to maintain that. So we're going to do that mapping here, right? But you see this inside IP, it's going to get translated different inside IP here, .20. It's going to get translated to the same public IP with a different port number assigned to it. And we're going to maintain that. We're going to keep track of those translations. And then when we talk to the outside, whatever we're reaching a web server, so port 80, but when we talk back, when the web server responds, right, so it's going to have this layer 3 packet, which is going to have its source IP, its destination IP, but then the layer 4 header in there, the source port is going to be like 80. The destination port, if it's responding to this IP address, is going to be 3000. Hold on, that looks so bad. I have to fix it when I have bad handwriting because I get comments on my YouTube channel saying everything's good but the handwriting's awful. So then when we receive that, we say, okay, the destination IP is me right here. But what's that port? Oh, 3000? Well, port 3000 is mapped to this private IP. So I'm going to then send that web server's response back to .10. And that's that. Okay, so I hope that's not too confusing. You know, when I first learned this, it was a little confusing for me with all these different terminology, like inside local, inside global are different, but then outside local, outside global is the same. Like, how does that make sense? It's just kind of going through the phases, right? Like the layer 3 packet, the original one generated by the PC, is going to be this as the source, this as the destination. Then once it crosses on the outside interface, right, towards the ISP, we get essentially a new layer 3 packet, essentially. We get a new layer 3 header, that says, hey, this is now our source IP. And yes, our destination IP is still the same, but we pretty much are getting a new layer 3 header now because I just translated these two addresses, okay? All right, now let's move on. All right, so now let's go over first hop redundancy protocols. So to talk about first hop redundancy protocols, I'm going to go ahead and go to our whiteboard because we're going to talk about two of the major protocols in first hop redundancy because that's what I know by heart. I do know about GLBP, but I don't know it as well as I know HSRP and VRP, so I'll go ahead and use the PowerPoints for that. But what is a first hop redundancy protocol? A first hop redundancy protocol is going to eliminate the single point of failures in our default gateways. So remember, this is first hop redundancy protocols. Each first hop redundancy protocol is going to accomplish the same thing. It's going to take two layer 3 routing devices. I'm going to do a multi-layer switch here. And it's going to allow us to have redundancy in the default gateways for our users. So let's say, actually, let's draw a campus network here. Have our access switches. We have our redundancy in our physical, right? Our layer 1. This is distro switch 1. This is distro switch 2. And let's say we have VLAN 10. we have VLAN 20. So here's the IP addressing for them. Then VLAN 10 is 10. Actually, let me make this a little bit more clear. 10.10.00/24. Okay? So we have two VLANs here. And now let's say we have our users. So we have a user over here, PC1. It's part of VLAN 10, so it's 10.10.0.50. And we have PC2. And its IP address is 10.10.0.60. So which one's the default gateway? Well, we haven't talked about this yet, but in these distro switches, you're going to have what's called SVIs, switch virtual interfaces. And each one of these distro switches could potentially be connected to your internet. So we could have a design like this. I'm going to get rid of the router. We're going to say this is the internet. So now how do we choose which one's going to be our default gateway? Well, if we each say that, hey, distro switch 1 is going to be the king, it's going to be the default gateway, that's fine. So we'll forward all traffic to distro switch 1. Distro switch 1 is going to have an SVI on there that's going to be doing all the routing for us. An SVI is a switch virtual interface that allows a switch to have an IP address and do IP routing. That's all good and fine. But then what happens if, God forbid, right, this distro switch goes down? Well, if we left that as our default gateway, now all of our users are hard down, even though we have another potentially layer 3 device that could route us out to the internet. So what's our solution? You guessed it, a first hop redundancy protocol. So we have first hop redundancy protocols that can take two layer 3 devices and make one a primary and one a secondary, or one an active or one a standby, or one a master and one a backup. What we mean by that is we could enable a protocol like HSRP or VRRP, hot standby redundancy protocol, or VRRP, which I think is the virtual router redundancy protocol. Don't quote me on that. We're going to look at the slides, but they do the same thing, okay? HSRP is Cisco proprietary, and this is an IEEE standard, which pretty much means non-proprietary, okay? And what these redundancy protocols are going to do is they're going to set up a virtual IP address between the two of them. They're also going to have a virtual MAC address between the two of them. And then we're going to elect one as the active and one as the standby. So each switch is still going to have a physical IP address. So distro switch 1 could be SVI 10, and that could be 10.10.0.2. Distro switch 3 could have SVI 10, and that could be 10.10.0.3. But then they both recognize that they're going to have a shared virtual IP address that, you guessed it, is going to be the default gateway. They're also going to have a shared MAC address. There's going to be a MAC address standard for each one of these protocols. And now at the PCs, all they know is that the default gateway is 10.10.0.1, 10.10.0.1, and they're just forwarding 10.0.0.1. And whatever this virtual MAC address is, this is not the actual MAC address. This isn't a CCNA course. I didn't want to, we don't need to know that standard, but whatever it is, right? And so when they build their ARP tables, they're going to say, hey, this MAC address belongs to this default gateway IP, and they don't know what's happening up here. But distro switch 1 and distro switch 2 do, because they have enabled HSRP or VRRP between each other that did a neighborship and then formed and then elected an active. So now up here are two layer 3 routing devices. Distro switch 1 became the active, distro switch 2 became the standby, and they say, hey, if I come down, distro switch 2 take over as the active, and we should have minimal downtime. And even if we do have minimal downtime, we're not hard down, because now distro switch 2 is going to take over this role of forwarding traffic, and now this devices down here have no idea that now actually distro switch 2 is forwarding traffic, because it's going to take over as this virtual IP, and that virtual MAC can become the active. So HSRP, VRP, and even GLBP accomplish the same thing. GLBP, the only difference is we can have more than just two devices, and we can also do load balancing with GLBP, but all three of those accomplish the same thing. What I just drew up here, they share a virtual IP address, virtual MAC address, and they're going to choose one to be the active or standby or master and backup, whatever terminology. We'll look at the slides because HSRP calls it something different than VRRP. And that's what our first hop redundancy protocols enable us to do. Now, I drew distro switches, but these could also be routers as well. Okay, so let's go ahead. And another thing, guys, if you purchase our self-paced training, I'm going to have bonus videos going over this, going configuration, HSRP and VRRP. Okay, so HSRP, hot standby router protocol. Routers in the HSRP group, so R1 and R2 here, they are going to do HSRP between each other. So they're going to be part of group 14, so that has to match. So essentially on their default gateway interface, say interface gig 00 on both, you type in standby group 14, that enables it. And then you have to type in standby 14 IP and set the virtual IP. So they're going to elect one as the active, one as the standby. And HSRP, the highest priority in the group becomes the active router. And if the priorities are equal and the default's 100, the router with the highest IP address. So in this case, R1, R2, their physical interfaces are going to have an actual IP address set. And if their priorities are equal at 100, the default, R2 will become the active because it has the higher IP address between the two interfaces that are doing HSRP between each other. Higher priority wins. We could hard set it. We could have made R1 the active if we said, hey, standby 14, that's our group number, priority 101. And then it would have became the active during their HSRP election. VRP, the Virtual Router Redundancy Protocol, I got it right. Same thing, provides redundancy for default gateways. It's non-proprietary, it's an IEEE standard. And here we call it master and backup, and it's going to do the exact same thing. Their MAC addresses will be a little different. There's like MAC address standards, right? So you always know, like if you're in HSRP and you do show ARP on your PC, you can tell if you're doing HSRP or VRP because they have their default MAC address standards, okay? And I have them drawn there. But there's a version 1 and version 2 for HSRP. I believe this is, I can't remember off the top of my head, this is version 1 or version 2 MAC address. Anyways, does the same thing, okay? There's a priority. If you pick a higher priority in VRRP, guess what? You're going to become the master. If your priorities are equal, then the higher IP address is going to become the master. And yes, my diagram is wrong. I will definitely fix that because for our downloadable content. All right, one I didn't talk about was GLBP, and that GLBP does the exact same thing except it can do load balancing. You have active virtual forwarders in there, and then you have the active virtual gateway. So if you're not doing load balancing, you have that active virtual gateway. If you're doing load balancing, you have active virtual forwarding, and you can have more than 2 devices in GLBP. Now, before we move on to our quiz, let's go ahead and take a look at our sub interface here. I am going to open up Secure CRT. I'm going to hop into this router here. I want to show you what a sub interface does. So if I'm on a Cisco device here, okay? So this syntax, I don't know, right? I haven't sat for the N10-009 test yet, and even if I did, I couldn't say. But I don't think there's going to be questions on Cisco syntax. So we're just going to take a look at this as an example, okay? If you're in a different environment, Juniper, Aruba, HP, anything else, and the syntax may be different. You may not even have CLI, may all be GUI, but sub interfaces generally do the same thing amongst all routers. They're going to be able to take this physical interface and create logical interfaces here that can do communication on the LAN between VLANs. So you see I have sub interface 10, 20, and 30. These numbers are actually irrelevant. These are just something administrative that you set. But .10 here should be doing my default gateway and routing for VLAN 10. The reason I know that is if I do show run interface gig 0/1.10, this command here, encapsulation .1q10. So that's saying, hey, if you see an 802.1q tag traffic coming into the interface and its VLAN number is 10, you're the default gateway for it. You're doing routing for that VLAN. So if we look at 20, it does the same thing. Look at 30, we have the same thing. So these sub interfaces, I numbered them to correlate, but this is really the command here that says, hey, you're doing routing for this VLAN. Because if you see a frame come in and you see its Ethernet headers tagged with 10, and the IEEE standard, you're the default gateway. So that's what sub-interfaces enable us to do in our routers. All right, now let's go ahead and do our quiz. All right, so I'm at our learning management system here. So this is, if you pay for our self-paced courses, this is what you're gonna get available to you for lifetime access. So I'm gonna go to my Net Plus course, go to my lessons here, and here I have day 8 is our routing technologies. And once this video is done and recorded, it gets uploaded as well. But we're gonna scroll down here and we're gonna take our domain quiz. All right, awesome. So let's go over these questions. So again, this is gonna be the quiz for our previous video as well. So if you're watching this video and you're like, hey, I didn't learn about static routing, you gotta go to the previous video. So question 1, which of the following is true about static routing? It doesn't automatically update, it doesn't use routing protocols. Static routing is manually configured by a network administrator. Question 2, which dynamic routing protocol is most commonly used for routing between autonomous systems on the internet? So they're talking about like between ISPs, so BGP, right? Because all these other ones are IGPs, interior gateway protocols, usually used between an intranet, enterprise, autonomous system within the ISP. But routing between autonomous systems on the internet, that is always BGP. That's an exterior gateway protocol. That's our internet routing protocol. Question 3, which first hop redundancy protocol is an open standard and not proprietary to a specific vendor? VRRP. Question 4, in HSRP, which router will take the role of the active router? The router with the highest priority, right? And if the priorities are equal, it's the router with the highest physical IP address. IP address on the physical interface, I should say. Question 5, which metric is used by OSPF to determine the best path to a destination? Bandwidth. It's called cost actually in OSPF, metric, right? But it's called the OSPF cost. The lowest cost is the best, and we determine the lowest cost by taking a reference bandwidth, dividing it by the actual bandwidth. The set standard is 100 megabits divided by your actual bandwidth, but obviously we know our bandwidth is much higher than 100 megabits, so we sometimes want to change that to like our reference bandwidth is 10 gigs. Anyways, it'd be crazy if I got that wrong, so I should probably fix this quiz. No, I read this wrong. Well, you got some learning out of it. It's trying to say, hey, like the metric is called cost, and lowest cost determines the best path. But it didn't ask me for the formula to determine cost. So that was a good trick question. English comprehension. Typically based on bandwidth of the links. It got me. My own quiz got me. Can you believe that? It's because I made the quiz like 5 days ago. Okay, question 6. What is the primary benefit of using network address translation? It allows multiple devices to share a single public IP address. So that's kind of PAT, right? Port address translation, which is just, that's based off NAT, right? Network address translation, that's what PAT is based off of. Question 7. Which of the following protocols provides both redundancy and load balancing across multiple routers? That is GLBP. So that is the Gateway Load Balancing Protocol. So it does do the same thing all the other first hop redundancy protocols do, except it also provides load balancing. It's going to have those active virtual forwarders. I hate when we don't get 100s, but 86, I think you'd pass, right? All right, guys. So awesome. I want to thank you all for viewing. Do not forget to like and subscribe, share with your friends, and I'll see you in the next section. We go over switching technologies.